So we just finished up our curve number infiltration and our Horton infiltration, and now we're going to shift gears and show you how to use the green Ampt infiltration calculators. The green Ampt system is a little more complex, so I'd like to first go over the global infiltration parameters. So if you open the global infiltration button, you'll see that you can check the green Ampt, and these default parameters can be modified by you per your project. These, I think, are the parameters recommended by the Flood Control District of Maricopa County. So for the initial abstraction, it's set to 0. We don't take out any additional initial abstraction through the global. Soil porosity is set to 0.4. This is your global hydraulic conductivity. It's set to 0.1. And initial saturation, final saturation, soil suction, and soil depth. Now I want to hover over each of these. So initial abstraction is in inches or millimeters. The average hydraulic conductivity is inches per hour or millimeters per hour. The hydraulic conductivity adjustment is an adjustment factor that you can use to maybe help tune in your infiltration to another event, such as a calibration event, but typically would use it set to 0. The initial saturation is the volume of the water over the volume of the void when the simulation starts. And the final saturation is the volume of the water over the volume of the void when the conditions are saturated, and so that would usually be 1. And then the soil suction will be in inches or millimeters. That's your capillary head. And your soil depth is a limiting depth variable, but for the global, if you want to apply that limiting depth, you have to set this soil D equal to something other than 0. So if the soil D equals 0, you have unlimited infiltration. And if the soil D is set to 0, that means you will not be using the spatially variable soil depth. So why don't we set ours to just 1 foot for the time being? And then we click OK, and we can continue on with the rest of the processing tools. So let's go open the Self-Help Tutorials, Lesson 1, Hydrology, and we have a handful of shapefiles down here. I'll go to External Layers, and then let's grab these land use, soil, and soil shapefiles. And I'll drag those onto the map, and then we can minimize this and start to look at these shapefiles. So the land use shapefile, in this case, is provided by the Flood Control District of Maricopa County. They provide the land use and soil maps for the projects that their clients run. But we will be using their data, but then we're going to show you how to get this data for anywhere in the United States. So let's open the land use layer and look at the attribute table. So from the land use, you get initial abstraction, temp, this is vegetative cover, but we don't use it. We're not going to use it in this example, so you can just ignore it. And initial saturation. This initial abstraction is a value in inches. This temp is a percent impervious of the polygons that are in this layer from 0 to 98. Flow 2D impervious is 0 to 1, but this value is 0 to 100. This is also a percent coverage, but like I said, we won't be using it, so we can skip it. And this is your initial saturation condition, which your initial saturation condition can be dry, wet, or normal. And that's the land use layer. This is the 2018 Flood Control District method. So in Maricopa County, this was the method they used as of like last year and previous years. This has a impervious related to rock outcrop, so that's your soil impervious. And this is your XK sat of hydraulic conductivity, average hydraulic conductivity of your soil layers. And this is your soil depth. And so in this method, they really are kind of assessing the first few inches of soil horizon. So it might be like the first 3 to 6 inches of soil horizon. And that might help you determine which soil depth to use. And they have really excellent hydrology manual the flood control district that you can get online, so you can learn how they develop these values. This is the 2023 method. Well, actually, let's see. So we got the PSIF. This would be the natural R temp and the hydraulic and the average hydraulic conductivity, and then we should have d theta normal and dry, and d theta normal and dry, and of course d theta wet is 0. So this data would be calculated or estimated by known factors of the soil horizon, you know, that upper soil horizon. So all of this data is, it's not available from the SUURGO, but you can get it from SUURGO by applying some algorithms and calculating it. And we have a tool that does that. But again, if you're working in Flood Control District of Maricopa County, or if you're working in Arizona, they have a soil layer for Maricopa County, and they have a soil layer for the state of Arizona that has these factors in it if you need them. All right, let's take a quick look at the first tool. The first tool will calculate the first tool will apply the 2018 flood control district method, where we don't apply the log average calculations and we don't apply the vegetative cover algorithm. So in this case, we need to set up the soil layer, and in this case we're going to be using the 2018 method, so we'll use the 2018 data. And we can set this to XKSAT, or hydraulic conductivity. This can be set to rock outcrop, and this can be set to soil depth. And these, you don't have to set these to anything because they're going to be skipped because we have unchecked this box right here. Now for the land use, that goes to land use 2018, and we will start with the initial saturation. We don't need this one, so leave it alone, it will be skipped. Initial abstraction, and the percent impervious from the land use layer, and then we can click OK. Now while that's calculating, let's go check the manual for this so you can see some of the way this data is processed. This is the Flow2D Technical Reference Manual, and I've added it to your list of manuals that are sent out with the demo model. And if you come to the, let's just look for the word green real quick, and if you come to the table of contents, you can see that we have the 2023 method, and it defines all the calculators, and the 2018 method. So let's go to the 2018 method while our calculator is running, and then we'll come back to it. So for the 2018 method, you can see here that you keep the box unchecked, and instead of processing these d theta and PSIF fields, it's going to calculate the PSIF and d theta as a function of the XKSAT. Okay, so it's a function of the XKSAT. And that is the only thing I wanted to say about the 2018 method. Now I can hear that our processor is done. So if I come back here and click OK, we can export this infiltration file. Don't forget, of course, you want to turn your infiltration switch on before you export it. So you turn your infiltration processor switch on and save it. And then let's click the export, and we want to export the .dat files, and we're still exporting straight into this lesson 1 export. So we select the folder, and we'll just do infiltration like we've been doing for the other 2 videos, and click OK. Click OK again, and now we should be able to go to that export folder and look at that infiltration.dat file. Well, it's actually going to automatically load because the Horton one was already open. So as soon as I click yes, it's going to open the new file. And let's just take a quick look at some of these variables. So this one is green Ampt. That means the switch is equal to 1. So that means we'll be using green Ampt. These are the global parameters that we looked at in the in QGIS global parameters window. And these are the local parameters. So let me open the data input manual, and let's take a quick look at, let's maybe minimize this a bit, and let's put these side by side, and so we can look at some of these parameters. So infiltration method here, well, hang on, let's do this. There we go. That's better. Okay, so your infiltration method is here, and your line 2 is related to green and Ampt, so it's initial abstraction, initial saturation, final saturation, porosity, soil depth, and we don't have a channel, so that's set to 0. Initial initial abstraction, initial saturation, final saturation, porosity, soil depth, and no channel, so that's set to 0. And we won't be turning on infiltration because our channel has a concrete lining on the bottom of it. We also have on line 3 the global hydraulic conductivity. I think this is the global soil suction, and the hydraulic conductivity adjustment, which we left off. We are not making an adjustment. Then we have this line of data, which is the infiltration character F, just indicates that it's a new line of data. Then here's your grid element number, and then there's the local hydraulic conductivity for that grid element, the local soil suction, local d theta, initial, let's see, that's initial abstraction, local, so that will be replacing this one, the local R temp, and the local soil depth. Now remember, if you don't set a soil depth, it will not use this value. So you have to set a global soil depth in order for it to use a local soil depth. Now if you look at these, if you want to learn more about these individual variables, you can come down to the file description and you can get information for each of these variables. So here's your d theta right here. One is a d theta global, or let's see, what is this one? This is the grid element d theta, grid element deficit, and this is the d theta for the channel segment. Let's see, this is the hydraulic conductivity for the grid element, so this is local, and this is the global hydraulic conductivity. And then he shows you the range of values that you might see, and the units, and tells you if there's extra information to see comments 2, 4, and 5. So if we go down to comments 2, 4, and 5, you'll get more instructions related to that, those 3 parameters. So 2, 4, and 5 are the comments that are associated with that hydraulic conductivity. So that's how you can review your infiltration data. Now let's take a quick look at the other method, which is the 2023 method. Okay, so in the 2023 method, let's turn off this shapefile. And in the 2023 method, we will have the same land use data, but updated soil attributes, which we already saw, so I won't bother looking at those again. So now when we click the Calculate Green Ampt button, we need to change our soil layer to 2023, and we need to set up the fields again. So hydraulic conductivity, rock outcrop, which we call R temp, soil depth, d theta normal. Be careful about this. Be sure to get the d theta n, and d theta dry, and this is the PSIF. Okay, and then we leave this checked on because now we are going to calculate these fields from the shapefile. Using this one will be using the log area average, and this one will be using just a regular area weighted average. Then our land use data. Remember, the initial saturation is tied back to the d theta normal or dry. So if your if your land use polygon is set to d theta normal, then it will intersect to the soil polygon, and it will apply the d theta normal for the soil polygon. And then what do we get? Then remember, please uncheck vegetative cover. And then initial abstraction is just a, I think it's a log area average too. We can check the manual. And then impervious is an area weighted average. But this impervious has to be kind of coupled back to this impervious. So meaning that the land use and soil layer will be intersected together, and a maximum impervious will be computed from those 2 layers. Now as I click OK, it's going to start the calculator, and we can now go and look at the plugin technical reference manual. But let's go back up to this Green Ampt and let's now look at the 2023 method. So what this is going to show you is what the individual calculators are doing. So your XKSAT is a log area average, where the area of these polygons is averaged, the log, and then the log XKSAT for those sub areas are then combined and put over the average grid element area. So you'll get a log area average for XKSAT for each individual grid element. And so of course, if one grid element is just inside here, there's no log, right? But if you have a combination of the two areas on a single grid element, that's where the log comes into play. Now for the PSIF, it'll be the exact same calculation, just performed on a different column of data. And then for the d theta, it's a little bit different because we do have to intersect d theta to the land use layer first, so that we can determine which which d theta column to use. So it'll either be d theta normal, wet, or dry, and of course d theta wet will be 0. So this would be your land use data, and this would be your d theta. So you would intersect these two layers together, and then your d theta would be assigned to these polygons, intersected to these polygons, and then assigned to your grid as an area weighted average. Okay, now let's see. Our temp is a little bit different. So our temp, again, we will be intersecting the soil layer to the land use layer, but in this case we'll be intersecting the impervious columns. And then we will take the, for each individual grid element, we will take the maximum of the R temp from the land use versus the R temp from the soil. So that's how this one works. And I think, vegetative cover, again, we don't use it, so I'm going to skip it. And then initial abstraction, it looks like it is just an area weighted average. So it's just an area weighted average only coming from the land use layer, so you don't have to intersect the land use to the soil layer. You're just intersecting the land use to the grid layer for the initial abstraction. And then of course we've already filled this out. Oops, sorry, that's the 2018 method, so I'm actually done. We come back here and finish, click OK, and then you can export that data again. And it should be slightly different because its initial abstraction should be the same. Its PSIF and d theta will be different. Its R temp should be the same of the 2018 method. So I'm not going to do that because you're just going to need to do it on your own. But instead, I want to show you the final method for calculating Green Ampt data, and that is to use the SUURGO data and the OpenStreetMap land use data and the SUURGO soil data. So Robson has applied a methodology that was created by J.E. Fuller for the Arizona Department of Transportation and for the state of Nevada, where they build a database of Green Ampt data for the whole state. Well, what we've done is we've built a microprocessor to do the same thing except for your project area. So if you don't have a project in Nevada or Arizona, you don't have Green Ampt data readily available. You can use these calculators. This one is going to go on to the SUURGO site, and I'm going to click yes to save in temporary. You know what? Hang on. I can't cancel. I'm just going to click yes. And now it's going on to the NRCS soil survey database, and it's downloading the data that it uses to build the soil polygon. It doesn't take very long because it's a pretty small project. But in the SUURGO data, you get a lot of different data sets. And we need data from 3 of them. We need the horizon data, the fragmentation data, the component data, and then this, I think, becomes our land use data that we want to use. And then this one, we're going to do the same thing for the OpenStreetMap data. Now this is going to go onto the OpenStreetMap layers, and it's going to download the data as rasters, and then it's going to read those rasters for colors and convert them into polygons, and then apply the colors of the raster as your land use categories. So you're getting a lot of different layers downloaded as rasters. Sorry that it's such a huge amount of data. Then it's vectorizing the cover map, and then so let's do this. Let's collapse all. Whoops. Oh, then I need to click OK so we can start the calculator. Let me just click cancel. We'll come back to the calculator. Okay. Let's do collapse all, and then let's take these layers and put them back down here in our external layers group. Now so this becomes our land use layer, and this becomes our soil layer, or actually I guess it's going to be this one. So let's take these guys and remove them, and then let's just focus on what this did. So guessing, I don't exactly know. I think you'd have to read some of the documentation that goes along with this data downloading tool to see what exactly it is that Robson's doing, but basically he's downloading different colors from the OpenStreetMap, or he's downloading different levels of the OpenStreetMap, and different layers of the OpenStreetMap represent different features. Buildings, streets, surfaces, parks, open areas, open parking lots, paved surfaces, things like that. So what Robson is doing is he's downloading all these different layers that represent like agricultural land or water, open water, or dry land or something like this. And then he's using that to develop a land use raster, and then that is going to be converted into a land use layer. Did I just remove that layer? I think I just removed the layer. Yeah, I did. Sorry about that. I'm going to have to rerun that one. Oh, I shouldn't have saved that this time. It's already been saved. I hope that doesn't cause an error. Let me pause this until I get that layer back. Okay, sorry for that delay. Now I got my land use layer loaded back onto the map. And so what Robson did is he converted all this data, and then he used raster calculators to calculate those land use characteristics. And then if you right click this and open the attribute table, you'll see that you have the initial saturation condition, the vegetative cover, the percent impervious land use, the initial abstraction, and I don't know what the DN stands for, so I'll just not worry about that. And then these are the three fields that we need for the calculator. So that's how the OpenStreetMap downloader works. Now I'll remove those layers, and the next one comes from the soil data. So what you get for the soil layer is you get a couple of extra fields, because we use these fields to calculate like the values that we're going to be using. So hydraulic conductivity is going to come from maybe the horizon layer of the SUURGO data, and the d theta normal and d theta wet would be derived from some of these other variables that are going to be coming from the component data, the SUURGO data, or maybe the fragment data. And then this would be, what is that? Is that that's probably some kind of saturation condition. I don't know what that variable stands for. And then your PSIF would also be derived from these other intersected tables. And then the sea horizon, I think, is responsible for rock outcrop. No, I think that one's component. Component is responsible for rock outcrop. So then you get all of these layers, and when you open your calculator back up, it's already set to calculate your layers. Of course, I dropped that one accidentally, so I'll have to set it back up. So that goes to saturation, uncheck that, FID, initial abstraction, and impervious area. So that comes from land use, and this one comes from the, sorry, I'm supposed to put that to the soil layer, and this one would go to hydraulic conductivity and rock outcrop, that would be PSIF, or no, our temp natural, and soil depth, and d theta normal, d theta dry, and then the PSIF. And then you'll click your calculator again and run that straight from your SUURGO data. So you can pretty much do that anywhere in the United States. Of course, you want to check your layers, make sure that they made sense. So the way to do that would be to go into your final infiltration table and sort your data columns high to low. So I can do that. Let me see if I can. What I'd have to do that is to turn on the advanced layers. So to turn on the advanced layers, you're going to go to Flow 2D settings, check advanced layers, and click OK. And now we have some advanced layers that we don't really want you messing with, but every once in a while you need to get in here because you need to delete these clear out data out of these layers. So if I open this attribute table, you can see that you can sort this data. That would be sorted by FID. This would be sorted by grid element. This would be sorted by hydraulic conductivity. This would be sorted by soil suction. This would be sorted by d theta. This would be sorted by initial abstraction. This would be sorted by percent impervious. See, the Flow 2D variable is is a decimal percentage. And this would be sorted by soil depth. So you can check your layers really quickly and easily, or you can do, statistics and things on these tables very quickly because they're part of Flow 2D. I'm sorry, they're part of QGIS. I would say one thing that you want to be cautious of is always sort back to FID, because the next time you export this data, if you were sorted by something else, it might export the data wrong. I'm not sure. It kind of depends on the exporter. They all work a little differently. Anyway, and that is green Ampt infiltration data. So that is the end of this video.